Okay, now let's look at some practice problems for the chapter of 1D motion. The first question, the one-dimensional position vector of a car is given by xt equals this expression here, 40 meters minus 20 meters per second times t plus 4 meters per square second times t squared. Question A, discuss the car's motion at t equals 0 second. Now, before we do that, let's practice our calculus skill. So let's do the derivative. So the velocity equals dx dt equals, now first term is constant, so it will fall out. The second term is negative 20. Remember, we need to also keep its unit. Plus the last term, we need to bring down a factor 2 here, so we get 8 meters per square second, and then times t. And if I carry out this derivative further, then I have ax equals dvx dt, second derivative, and then I will get rid of this first term. The second term is 8, becomes a constant 8. Now we can answer question A. Okay, so the car's motion at t equals 0 second. We need to plug in t equals 0 second for the x. So x when t equals 0 second equals only the first term stay. So let's write this down, 40 meters. And the velocity at 0 second equals negative 20 meters per second. And then the acceleration at 0 second equals a constant 8 meters per square second. Now we can give this object's motion a drawing. So let's say we have x-axis pointing this way. That's the origin O, and then the object starts at 40 meters. So that's the initial position. And the velocity is negative, so it's pointing this way. Let me see, maybe just write down the numbers here. Negative 20 meters per second. And then the acceleration is to the right. Positive 8. Now question B, find the leftmost position of the car and the time for that. So now we know the acceleration is opposite the velocity, and it's going to reduce the magnitude of the velocity, right? You can say decelerate. So the car will decelerate until the instant when its velocity becomes 0, and that will give us the leftmost position. So we can kind of draw that position. It must be somewhere here, or maybe also exceed the origin, go to the left side of the origin. But now let's say it's here, and that will be the instant when the velocity becomes 0, and that will be the leftmost position. Okay, so that's why it's important to figure out the instant for the velocity to become 0. And we have conveniently the expression that we have earlier, Vx equals that. So if I set it to 0, then I can solve for this instant t. Okay, so also for convenience, I neglectly writing down the units. But if you keep everything in SI unit, you will get the unit naturally from the calculation. So for example, here I can solve for t, and then I get 20/8, which is 2.5 seconds. Now you see I put back the unit. The unit is SI unit as well, which is second. So that's the instant. And when I plug in the t's value for the x here, then we'll get to the leftmost position. So leftmost position. X, let me call it x left equals 40 minus, from this expression, 20 minus 2 times 2.5, and then plus 4 times 2.5 squared equals so this number is 15 meters. Okay, so that's the leftmost position. Now I can put in the numbers here. 15 meters. Okay, so now you see the object move, the car moves from 40 meters to 15 meters, and then it will turn around. Okay, so that's the also so-called turning point. It's defined as the velocity becomes 0. Okay, so now with letter, now we can figure out the car's motion picture. So we have a car moving this way at the beginning until this point, and then it will turn around, moving the other way. Okay, so let me call the first movement delta x1, second displacement delta x2. So delta x1 is the displacement from the initial position to the leftmost position. Delta x2 is from the leftmost position to a final position. Okay, so I can write this down. So that's for answer question C. I forgot to mention that. So delta x1 is given by, this displacement is given by 15 minus 40, right? 15 is the final position, 40 is the initial position. So the first displacement is negative 25 meters. The negative sign means that the displacement direction is to the left. Okay, so now the second segment of the displacement would depend on whatever we calculate for the final position minus 15. That's the initial position for the second displacement, and then we'll get a number there. Okay, so let me figure out this t equals 4 seconds first. So x for 4 seconds equals, you plug in 4 seconds here, 20 minus times 4 plus 4 times 4 squared equals, okay, so this number is 24 meters. So now I can plug in the numbers here, 24 minus 15, so we get 9 meters. So 9 meters, which is positive, is the second displacement. Now the question does ask us about the displacement, right? Total displacement. So the total displacement, delta x, is delta x1 plus delta x2 equals negative 25 plus 9, and that gives us negative 16 meters. Okay, so the total displacement is negative 16 meters. But you also ask us about the distance traveled. Okay, so I'm going to use a symbol S here to represent the distance. So the distance will be the delta x1 magnitude plus delta x2 magnitude, and that gives us 25 plus 9 equals 34 meters. Okay, so when we talk about the distance traveled, it will be car going to the leftmost position and then return, and then we need to sum up those distances. Now if we calculate the average velocity and average speed, then we need to, let me use the different symbol here. So Vx average will represent average velocity. So it's given by delta x over delta t. Now we have negative 16 for the delta x. Delta t here is 4 minus 0. So it's 4 seconds, right? So we get negative 4 meters per second. So average velocity is negative, meaning in the end, the object moved to the left side. Now the average speed, so let me call that Vs instead. Vs average. Okay, so now it's delta s. My symbol here is s, so it's s, simply just s over delta t. 34 over 4 equals 8.5 meters per second. All right, so that's the first question. Second problem. A stone is thrown straight up with an initial speed of 50 meters per second from the top of a 30-meter high building. The stone rises to the highest position, reverses its motion, and then moves straight down. When is the stone at the highest position, and what is the displacement for the stone at this position? That's the first question. Second question, when is the stone 10 meters below the top of the building? Let's draw a picture first. So here, let's say it's the top of the building. And I'm going to set this as the origin O. Okay, that's the initial position. And then I can draw a y-axis pointing upward or pointing downward. Okay, and both should give us the same result. So I'm going to, in this illustration here, I'm going to talk about first a y-axis pointing upward. And then in the next page, I'm going to talk about setting up y-axis as downward. Okay, so here is the upward direction for y-axis. Okay, now with that, I can write down the initial condition. So t equals 0. The position will be 0 here, and then the velocity will be positive 15 meters per second, right? Because it's upward, so it's positive. That's this velocity. Now, how about the acceleration? Here's the free fall. So the acceleration of the object is this way. Let me call it AY. Now, in this case here, since y-axis is upward, so it's negative g. Another condition that we know here for the question is negative g, or negative 9.8 meters per square second. Okay. Now with that, I can write down the final velocity as a function of the initial velocity plus the acceleration. And then I can figure out the highest point. The highest point is the point where we have velocity equals 0. So v1 equals 0 at highest position. All right, so let's put in the numbers. So we get v1 equals 0 here equals velocity, initial velocity is 15 times t, and then the initial the acceleration here is negative. Okay, excuse me, there's no t here. All right, so I can solve for the instant. Let me call this th. the highest point instant is given by 15 divided by 9.8 equals the instant here is 1.53 seconds. So at that instant, the object is at the highest point. Okay. Now, what is the displacement? So now I can calculate the highest position y equals the initial position plus Vy initial velocity's contribution plus the contribution from the acceleration. Okay, so we get 0 here for y0. Vy0 is positive 15 times the time, and then negative 1/2 9.8. So we know ay is negative, and then the time squared, and then in the end you will get the final position is 11.5 meters. Okay, so that's the y for the highest position. Let's call this question A. Now question B, when is the stone 10 meters below? Okay, so we know here is the top of the building, and when you throw an object up, the stone up, it will go down to the same level, right? But it will keep going down. Suppose that the object can go down. It's not blocked by the roof. Right? All right, so let's say it will go up and then go down. Now at this position, that's the final position. This y equals 10 meters, right? But now it's below the origin, so it's negative. So that's something you need to be careful about. The position here is a vector, so you need to include its sign, right? Whether it's above the origin or below the origin. Below the origin should be negative. Okay, so now we know y's expression is y0 plus, that's basically the same expression here, except that we change the th to t, an instant that we need to determine. Okay, and then we can plug in the numbers. So y equals negative 10, y0 is 0, Vy0 is positive 15 times t, and then negative 1/2 times 9.8 t squared, right? So I'm going to write this in the standard form. So I'm going to move this t squared term to the left side, so it becomes positive 4.9 t squared. 15t also to the left, negative 15t minus 10 equals 0. Okay. And then we know the solution to this quadratic equation. We continue here. So the solution is given by 15 plus or minus square root 15 squared minus 4 times 4.9 times negative 10. We need to keep the negative sign here, and then divided by 2 times 4.9. Okay. Now when you plug in the positive sign, you get a value which is 3.62 seconds. And when you plug in a negative sign, you'll get another value. It becomes negative 0.56 seconds. Okay, so I'm going to say this one is our solution, and that's unphysical because the time is always positive, right? So starting from 0 second, and then the future time will be positive. So it cannot be negative sign. Negative sign will mean the object, when I draw this trajectory, I need to draw it backward, right? So the object starts from here, then that's also negative 10 for the initial position. Okay, but that's unphysical. Okay, so I'm going to talk about solution to exactly the same question here, But now I'm going to set up the coordinate system to be downward, and you will see that it doesn't affect the final result. The final result is still the same. So let's see. That's the top of the building, and we're gonna say the origin O is here, and then the y-axis is downward. Okay, now initial velocity will be upward. Sorry, velocity. So it's negative. Okay, so let's change it from the previous value, which is positive in the previous coordinate system. So now this velocity is negative. Okay, now ay, when the object is in the air, experience ay equals, now it's positive g, right? Because it's in the same direction as the y-axis. So it's positive 9.8 meters per second, square second. Okay. All right, so let's also figure out what's the instant for the highest position. So we need a Vy, the final velocity in terms of initial velocity plus the contribution from the Ay. And when I plug in 0 here, I was plugging negative 15, and then Ay now becomes positive. The T is TH. That's the instant we call the highest position. So TH here is 15 over 9.8. Okay, so now you see it's the same. It's the same instant as before. So that means that the physical process here is not changed by the coordinate system that we set up. Coordinate system setup is arbitrary. Right? Some people use upward as positive, some people use downward as positive, but that shouldn't affect the same physical process that they both describe. So now we can also figure out the displacement. So now the y position will be y naught plus y naught contribution yh here. Let's plug in the numbers. 0 plus minus 15 times 1.53 plus 1/2 times 9.8. Now it's positive here. Now the answer here is negative 11.5 meters. Okay, so now it becomes negative because it's this direction, right? This position direction is negative. All right, so I hope that shows us the concept that the coordinate system does not affect the final result. Now, if you compare with the previous, we get the position here as positive. That's because we set up the y-axis to be upward, and now it's negative. Okay. However, the magnitude here does not change. Okay, so that's all for the second method. I want to just show you the effect of these y-axis. And it turns out to be no effect if you keep track of the signs correctly. Okay, so last question here. A car traveling with a constant speed of 31 meters per second is detected by a police officer at a highway where the speed limit is 24 meters per second. Just as the car passes, the police officer starts from rest in pursuit with a constant acceleration of 3 meters per square second. When will the police officer catch the speeding car? What is the speed of the police car when this happens? And what is the distance traveled by the police car? Okay, so we have two objects here doing 1D motion. And let me set up the coordinate system first. So now here is the x-axis. We can simplify it to be a straight line motion, but in reality, the road can be a curved path. Okay, but it doesn't matter. It's along the same direction. All right, so now we have a car, we have a police officer, and let's write down their known conditions. So the car is doing constant velocity motion. So its velocity, let's call it VC, is a constant, equals 31 meters per second in the same direction as the x-axis. And the car has no acceleration, right? So let's call this AC equals 0. And also at t equals 0, x car equals 0. Its position is at 0. Okay, so let's write down the police officer. The police officer's initial velocity, let's call this VP not equals 0, right? Because police officer stopped there and then start chasing later on. And its position xp naught is also 0. This one is xc naught. But the acceleration of the police officer is 3 meters per square second. It's a constant. So we can write down the displacement or final position for both objects. For the car, since it's constant, so we just need to multiply the VC, multiply t here, and then for the police officer, we can write down this quadratic equation. Okay, and then we need to set them equal, right? Because when the police officer catch the car, they're at the same location. Both police and the car they're at the same location, right? So that's why they're the same at the instant when the police officer catch the speeding car. So let's write this down. So we have xe not equal 0 for both police and the car, speeding car. So we have VCT equals police officer initial velocity will be 0 here, so that's why it's 1/2 APT squared. Okay, now this equation has two solutions. We can say t equals 0 second is the solution, but this one is trivial, right? Because we know that's the initial position of both police and the speeding car, so that's why they should have the same displacement. But we also have a non-trivial solution where we have VC equals 1/2 AP times T. So T equals 2 VC over AP. 2 times 31 over 3. Okay. Now the velocity here is, the instant here is 20.7 seconds. And now let's figure out what's the speed of the police car when this happens. So let me write down this velocity of police equals, the initial velocity is 0 plus AP times T. Okay, so that equals 3 times 20.7. So that equals approximately 62 meters per second. Now how about the distance traveled? Distance traveled for the police officer and for the car are the same. So that's why I'm going to just write down the final position or the distance using the speeding car times this t, right? Because that's easier. We have a single term there, and then VC is 31 meters per second times 20.7 seconds, and then that gives us 641.7 meters. Okay, so that's the distance traveled. These three numbers are the answers. Okay, so now let me briefly talk about another method for solving this problem, right? Because we know the displacement as a, here's method 2. So we know the displacement of the police officer is also given by the average velocity times t, right? So average velocity is the final velocity plus initial velocity divided by 2. Okay, so that's something that we talked about in the lecture, and then times t. So if I use this expression to solve for the final velocity of the police car, then it's much easier. So this xp equals xc equals vct. Okay, now t and t cancel out, so the police officer's speed is twice the speed of the speeding car, which is 62 meters per second. Okay, and then from there you can go backward and then solve for the time. The time would be the same as before. Okay, so just one more method here is, if you remember using the average velocity, then sometimes you will simplify your calculation. Alright, that's all for this practice problem video. Thanks for watching.